Quadrilateral PQRS is constructed with QR as 51. The diagonal intersect at 90 degrees at point T. PT is 32, QT is 24. Calculate the length of PQ. So PQ, of course, is going to be done with Pythagoras, and I think Pythagoras is the common theme in this question. So PQ squared is 32 squared plus 24 squared. And when you calculate PQ, this turns out to be 40. Calculate the area of PQR. Okay, so this whole thing, PQR. So I guess we will need to figure out first the length TR. So TR squared plus 24 squared is 51 squared, using Pythagoras once more. And when you calculate TR, it turns out to be 45. So now when we calculate the area of triangle PQR, it's really just 1/2 base times height. And the base is 32 plus TR, and TR is 45, so that's what, 77, I believe. And the height is just this guy, 24. So it's 1/2 times 77 times 24, and that turns out to be 924. If QS to PR is 12 to 11, determine the perimeter of quadrilateral PQRS. Perimeter this time, so not the area. All right, so first let's use what they gave us. QS over PR is 12 over 11. Now, I think one of these we know. QS, is it? No, QS we don't know, but we know PR. Yeah, PR we just figured out was 77. So QS over 77 is 12 over 11, and then when you solve for QS, you will get 84. Okay, so if QS is 84 and Q to T is 24, that means TS would be 84 minus 24, which I believe is 60. So put that in there. And then finally, the perimeter of PQRS. PQR, so the whole thing, I guess. Okay, so that perimeter, P, would be PQ plus QR plus PS plus SR. Okay, so let's see what we have so far. PQ, we know is 40. We calculated that. QR, that one they give us already. PS, okay, you can use Pythagoras again. PS squared is 32 squared plus 60 squared. And then when you do that, PS turns out to be 68. So put that in there. And then SR, okay, same thing. Pythagoras again, so SR would be 60 squared plus 45 squared, I believe. And then when you calculate this, SR turns out to be 75, I believe. Yeah. And then you just add these guys up, and when you do, you get 234. So that takes care of part C. Number 2, determine the value of a plus b squared, given that a squared plus b squared is 24 and ab is 6. All right, well, a plus b squared expands to a squared plus 2ab plus b squared. All right, well, a squared plus b squared, that is 24, so this guy and this guy is 24. And then 2ab, well, ab, they tell me is 6. So there you go. You just put that in there. So this is 24 plus 12, which I believe is 36. Yeah. Part B, if x plus y squared is 13, x squared plus y squared is 7, determine the value of xy. So same kind of story here. I think there's nothing different here. X squared plus 2xy plus y squared is 13. X squared plus y squared is 7, so this and this is 7. And then that just leaves me with 2xy. 2xy, therefore, would be 6, and then our xy would be 3. And that is what they wanted, the value for xy. So, as you can see, a little bit of algebra, and you can get it done. All right, next one. We have j and k this time is 6. J squared plus k squared is 52. Find the value of jk. So I think this is pretty much the same thing. J plus k is 6. So I'm going to square them. Both sides, I should say, and that's going to give me j squared plus 2jk plus k squared is equal to 36. All right. And if that's the case, then those two guys is 36, and then that just leaves me with 2jk is 36. Wait, is this? No, sorry. That's 52. Yes, shouldn't have made that mistake. All right, well, keep going here. 2jk. This is going to be a negative, interestingly. So that's going to be negative 16. And therefore, jk is minus 8. Yeah, minus 8. Okay. And then finally, we have this guy, d. If m squared plus n squared is 12, m to the power 4 plus n to the power 4 is 136, determine all possible values of mn. All right. So m squared plus n squared is 12. So I think, again, I'm going to square both sides following the theme of this question. So that's going to be m to the power 4, 2m squared n squared plus n to the power 4 is equal to 144. And then this helps us because those two guys are 136. So then we have 2m squared n squared is 144. All right, so that means 2m squared n squared would be what, 8? Yeah. And then therefore m squared n squared would be 4. And then if you take the square root of both sides, it's going to be mn is equal to plus or minus 2. And that completes this question. Points. M and n lie on the parabola y equals x squared. Determine the value of n such that angle MON is 90. All right, if that angle is 90, then that means those two lines that you can see are going to be perpendicular, and perpendicular lines have slopes that are negative reciprocals. So, for example, if one slope was, say, 4 over 7, the other slope would be negative 7 over 4. Now, negative reciprocals, when you multiply them, if you were to multiply these two guys, they would give you a product of negative 1. So that's what we're going to do. We're going to say that we have two slopes, m1 and m2, and when they multiply each other, you get negative 1. So let's do that. The first slope is this guy right here, and the other slope is right there, the one obviously that's perpendicular. So using rise over run, we're going to have n squared minus 0 over n minus 0 for m1, and then m2 would be 1/4 minus 0 over 1/2 minus 0. And all this equals negative 1. So this just reduces to n, and this guy reduces to 1/4 divided by 1/2, I believe is 1/2. Is that right? 1/4 and then 2 over 1, yeah, 1/2. When you invert and multiply. So that basically means that n is minus 2. Yeah, that's it. Okay, that's pretty easy. Okay, so the next one, same story, I think. Points A and B are endpoints this time. Same parabola. Determine the value of B if the angle is 90. Okay, so kind of same story here. We're going to have one slope, that one, and the other slope, that one, and they're perpendicular, so they're going to have negative reciprocals, and when you multiply them, they equal negative 1. Okay, so the first slope, using the b in the origin, that's going to be b squared minus 0 over b minus 0. And then m2 is 4 minus b squared over 2 minus b, like that. And that equals negative 1. So this is just going to be b, and this is going to be, I think this factors 2 minus b, 2 plus b, and then of course you got 2 minus b on the bottom, and that's negative 1. So that means that the 2 minus b's cancel, so all you're left with is 2 plus b times b. So that's going to be b squared plus 2b, and then I'm going to put the 1 on that side to make it an equation like that. And then this factors very nicely, I believe. I think it's just b plus 1 times b plus 1. And that means that b is negative 1. And I think that's it. All right, great. And then finally, we've got a right-angled triangle, this time PQR, inscribed inside y equals x squared again, as shown. PQR have coordinates as shown respectively, and PQR are integers, show that 2q plus p plus r is equal to 0. All right, so I'm not really sure what to do to show that, but I think I'm going to follow the same thing that I've been doing so far, and I think if I do that, I should be able to arrive at that somehow. And that is the same story where you take the two slopes and you understand that because they're perpendicular, their slopes values would, the product would be negative 1. All right, so let's go M1. Let's use, well, whatever. It doesn't really matter. We can use QR, that line. So that would mean Q squared minus R squared, and then Q minus R. And then M2, we use PQ. That's going to be P squared minus Q squared over P minus Q. And all that equals -1. All right. So this will factor, of course, Q minus R, Q plus R. And then this is Q minus R on the bottom. And then this will factor P minus Q, P plus Q, and P minus Q on the bottom. And that's -1. So this just reduces to Q plus R times P plus Q. And that's -1. All right, great. So now where do we go from here? Do we expand this? If we expand this, I'm not sure how we're going to get to that, because you're going to have a Q squared in there if you expand it, right? So I don't think expansion is the way to go here. This little clue, I think, is the key, that they're integers, P, Q, and R. P, Q, and R, those three are integers. So if that's the case, this actually has limited options. If this times this is equal to -1, that means either Q plus R is equal to 1 and P plus Q is equal to -1, or it could mean that Q plus R is -1 and P plus Q is equal to 1, right? Okay, so let's work with this. Let's first look at this scenario here, this guy. If that's the case, if you add these two equations, you will get 2Q plus R plus P is equal to 0. And that is what this is. All right, 2Q plus R plus, yeah. Okay, so that's great. If you add these guys, let's see, what do you get? You get 2Q plus R plus P is equal to 0. So either way, I get what they want me to show. The positive divisors of 21 are 1, 3, 7, 21. Let S at n be the sum of the positive divisors of the positive integer n. For example, S at 21 would be 1 plus 3 plus 7 plus 21, which is 32. If p is an odd prime integer, find the value of p such that S at 2p squared is 2613. All right. So first, I'll give you a little bit of a primer, just in the hopes that it will help you. So let's say you have a number, right? That's like a to the power of n and b to the power of m, where a and b are prime numbers. The number of divisors would be n plus 1 times m plus 1. So I'll give you a real world example. Let's say we have 7 to the power of 2 times 11 to the power of 3. And I said 2, how many divisors does this have? Now you can list them manually, or you can just do the trick. It's not really a trick, but the method, which is it's going to be 2 plus 1 times 3 plus 1, which in this case is 3 times 4, which is 12. So there's 12 divisors, and then you can manually list them. But it's a lot quicker to sort of just do it that way. So I wanted to show you that first. Okay, so let's go back to the question. We're going to need a little bit of space here, so let's move this up. We've got this scenario of 2p squared. Now, p is prime, right? Yeah, p is prime, I believe. Yeah, it's an odd, well, all primes are odd except 2. So now I'm going to give you an example first of how do I figure out the divisors of that? Well, let's say I had 17 squared times 2. And I said to find the divisors. Well, first let's just do 17 squared. The divisors of 17 squared are 1, 17, and 17 squared, right? Because 17 is a prime. Now if I tagged along a little 2 there and said find the divisors of this, again it's 1, 17, 17 squared, but then you have to add the 2. So you have also 2 times 17, which I believe is 34, and 2 times 17 squared. So you would have a total of 6 divisors. Yeah. Now, this is 2 to the power of 1, right? So that technique, it would be 1 plus 1 times 2 plus 1, which is 2 times 3, which is 6. And, of course, we did get 6. So both ways, we got 6. So in the same way, the divisors of this guy, if you follow the same technique, we were going to have 6 because this is 2 to the power of 1, right? So it's going to be 1 plus 1 times 2 plus 1, the number of divisors, and that's 2 times 3, which is 6. Now I'm going to manually list them. It's very similar to this. It's going to be 1p, p squared, 2p, and 2p squared. I think those are the divisors. Okay, now by our definition in the question, s at 2p squared is the sum of all those divisors. So it would be 1 plus p squared plus 2 plus 2p plus 2p squared. Okay, so far so good. Nothing fancy so far. And they tell me that this is equal to 2613. And let's add this up here. Let's see what we get. 3p squared, collecting like terms, 3p and 3. Okay, that's nice. A lot of 3's there. Let's divide through by 3, and the good news is it does. 871, p squared plus p plus 1. And let's put everything on one side. P squared plus p minus 870. And then let's see if we can factor this. 870, what is 870? And let's see, 870 is 2 times 5 times 3 times 29. So that's what, 30 times 29. Okay, I got it. I just want to do that, make it my factoring a little bit easier. 30 and 29, and then I think it'll be plus. Now we are into part B. The consecutive integers 14 and 15 have the property that s at 14 is equal to s at 15. Determine all pairs of consecutive integers m and n such that m is equal to 2p and n is equal to 9q for prime integers p and q greater than 3 and s at m is equal to s at n. So let's discuss this. We have something that is consecutive. So 14 and 15 are the examples they gave us. So 14, for example, has the divisors 1, 2, 7, and 14. So therefore, s at 14 is the sum of those guys, and that is 24, correct? That should be a 14, sorry. Yeah, 24. And then 15 has the divisors 1, 3, 5, and 15. And therefore, s at 15 would be the sum of those guys, which is also 24. So therefore, that means that s at 14 and s at 15 are equal. So they just give that as an example. Now they tell me that we have m and n. And m is equal to 2p, and n is equal to 9q. And then somehow, someway, we have to solve this with that bit of information. But they also tell us that m and n are consecutive. So that means if these guys are consecutive, this would be like m, well, obviously, and n is going to be m plus 1, right? It's basically the next number over. Okay. And then p and q are greater than 3, and then we have to show this. All right. Okay, so the first thing I'm going to write is s at m, and s at m is the same at s at 2p, because m is equal to 2p. And p and q are prime. Okay, so that shouldn't be that bad. So we have to just add up the divisors of 2p, and since p is prime, the only divisors of 2p are 1p, 2, and 2p. So just add these guys up, and when you do, I believe you get 3p plus 3. Yeah. And then s at n, well, n is 9q, so that's the same as 9q. And again, q is prime. So the only divisors of 9q would be 1, 3, 9, q, 3q, and 9q, I believe. Yeah. So this is 13q plus 13. Now, they told me that S at M is equal to S at N. So this guy is equal to that guy. So that means this is equal to this. So 3p plus 3 is equal to 13q plus 13. Now, anything I can do here, 3p minus 13q is equal to 10. All right, so that's about as far as I can go there. And I'm going to probably need to use this. So I'm just going to call that 1 for now. I'm most likely going to have to use that a little bit later on. Okay, so now where can I go from here? What more information? I know that these are consecutive, right? So that means we have n is equal to m plus 1. All right. Okay, so let me just substitute what they are in terms of p's and q's. N is 9q, and m is 2p. So that means 9q minus 2p is equal to 1. And I believe that is the only other equation I can find here. Okay. And I think that should be good enough to figure out this question. Just those two. Okay, so now I've got to solve. I've got two equations, two variables I can solve for p and q. Let's see, how can I combine this? If I multiply equation 2 by 3 and then add to it double of equation 1, I think that should do it. That's going to give me 27q. These two guys, this guy and this guy, just in case you're wondering. 27q minus 6p plus 6p minus 26q is equal to 3 plus 20. So that's going to give me q is equal to 23. And then if I substitute that back into either one of these guys, I can solve for p. And when I do, I get p is equal to 103. Okay. And then let's figure out what is m and n. Well, m is equal to 2p. So 2p would be 206. And n is equal to 9q. So 9 times 23 is 207. Okay. That those are consecutive. 206, 207 are consecutive. And what do they want actually? Determine all pairs of consecutive integers m and n. So they just wanted us to figure out m and n, and we did. We figured out that m is 206 and n is 207. And finally, part C, determine the number of pairs of distinct prime integers q and p, each less than 30, with the property that s at p to the power 3q is not divisible by 24. All right, so the same thing, by definition, s at p to the power 3 times q is the sum of the divisors. So we got to list all the divisors. All right, so I guess the divisors, let me just make a little example here. So let's say p was 17 and q was 7. Then p to the power 3 times q would be 17 to the power 3 times 7 to the power of 1. Now, using our little tool, we can say that the number of divisors is 3 plus 1 times 1 plus 1, which is 4 times 2, which is 8. So we got to come up with 8 divisors of that guy. And I think in this particular case, it would be 1, 7, 17, 7 times 17. Let's see here, 17 squared times 7, 17 to the power of 3, and 17 to the power of 3 times 7. Is that 8? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Okay, so the same kind of story here. I just wanted to put that in there just to make it a little bit easier, because you're using letters here. It might be a little abstract. So it'd be 1, it would be Q, P, PQ, P squared, P squared Q, P to the power of 3, and then P to the power of 3Q. All right, so we have to take this equation and manipulate it a little bit. And this is the very nice algebra. We just took this guy here, and we kind of factor it and eventually get down to a very nice, pretty final result. And this we will call our equation 1. And we want basically to show that this guy is not divisible by 24. And we have to figure out what are the values for P and Q for that to occur. Okay, so first of all, how many different types of, how many pairs are there in total for everything, like regardless of any condition? Well, for P and for Q, we have to list how many options there are. They told me that both P and Q are less than 30, right? And they're both primes. So first, let's list which primes are less than 30. We have 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. And the same story holds true for Q. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for P, we have 10 choices. And for Q, are they distinct? They're distinct. So Q cannot be the same as P. So if we have 10 choices for P, we would have a remaining 9 choices for Q. So in total, the number of pairs would be 90 of the form PQ. So that's the total. Then we have to figure out how many of those 90 are actually not divisible by 24. Okay. So what I'm going to do is actually, let's figure out how many are divisible by 24. And then I can subtract that from 90 to get how many are not divisible by 24. So let's do that. So we concentrate first on our equation, which I will write again. It was Q plus 1 times P plus 1 times P squared plus 1. And we got to figure out how many of these are divisible by 24, and then we can subtract that number from 90 to figure out how many are not divisible by 24. Okay, so a few cases. The case 1 is when we just concentrate on this guy here. Yeah, I think so. Okay, so I want to list these again. If we have Q equal to 23, 23 is one of the choices, right? Yeah. Then this guy would be 24, and there you go. It would be divisible by 24. So remember, we're concentrating on how many are divisible by 24 at this point. So that means anything of the form PQ, where Q is 23, I should say, would be a pair that would make this expression divisible by 24. Now P has P has actually 10 choices, but we can't use 23 because they'd have to be distinct. So we have 9 choices for this guy. So there's 9 of these guys, 9 such pairs. Yeah. Yeah. And I think the same story holds true for P. If P is 23, then again, this whole expression would be divisible by 24. So anything of the form 23Q would also work, where Q is anything except 23. So again, 9 choices there. So again, another 9 pairs of that form. Okay, so that sort of takes care of when you're looking at these guys individually. Next, I think I have to look at this guy over here. Yeah, but I don't think anything will work for P squared plus 1, so I'm going to have to probably include the P plus 1. Yeah. Okay, so let's do that. We won't forget this 9 and this 9, but we'll have to come back and add it later. So, as I stated earlier, we got to concentrate on this P plus Q, P squared plus 1 part of that equation, up there. Now, for values for P, remember, P has limited options, right? There's only 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9. But we already exhausted the 23 part. So that's why 23 is not included in our table. But all the other ones, we work with it and see what happens. If P is 2, then this expression right here would be 3 times 5. Now that's 15. Now that's not going to work. But if Q plus 1, this guy is, say, 8, then it may become a multiple of 24. And that happens when Q is 7. If Q is 7, then this guy up here becomes an 8. And then when you multiply it by 3, that 3 there, it becomes 24. So those are the two values for P and Q that make that expression divisible by 24. So when P is 2 and when Q is 7. And there's only one such ordered pair, that ordered pair being 2, 7. And then similarly, you just go through it. When P is 3, what happens? Well, this expression becomes 4 times 10, which is 2 to the power 3 times 5, whatever. And then in order to get it divisible by 24, well, we need to make the other side or other part of that equation, I guess, a multiple of 3, because this is 8. And if we have any multiple of 3, 8 times 3 is 24. So when Q is 2, for example, this guy here becomes 3. That works. When Q is 5, it becomes 6, which is a multiple of 3, and similarly 11, 17, and 29. So now we have 3 for the value of P, and any of these guys for the value of Q. So 3, 2, 3, 5, 3, 11, 3, 17, and 3, 29. So that gives you another 5 ordered pairs. So you see what's happening for each value of P. We got to figure out what Q should equal to make this big expression divisible by 24. And obviously, I'm not going to walk you through every single one, but this table lists them all, and it also lists how many ordered pairs you get for each scenario. And when you add all these up, you get 49. And then, of course, don't forget these two guys. So then you have to add those. So it's 49 plus that 9 plus that 9, and that's 67. Now, remember, these are the ones that make this expression divisible by 24. We want how many would not be divisible by 24. The total was 90. So you just subtract how many pairs would make that expression divisible by 24, which gives you 23. And these are the pairs that would make that expression not divisible by 24.